Right, so for the next talk, Daniel will tell us about typing strictness.
Thank you, and thank you everyone for coming. Today I'm going to be talking about my work with my collaborators at Penn on using type systems to model strictness. So in this talk I want to try to answer three main questions. First, what are strictness and laziness? Second, why would we model them with a type system and how would we go about doing so? And third, what properties would such a system guarantee? What benefit would we get from this approach? To begin answering the first question, I want to start by fixing some terminology. The words strict and lazy are used in rather overloaded ways throughout the literature, and I want to make sure that we're all on precisely the same page about what I mean when I use them in this talk. I'm going to use these terms in a couple of different but related ways, the first of which is as a characterization of evaluation strategies, not as descriptions of programming languages. A strict evaluation strategy is one that evaluates all expressions immediately as soon as they are encountered during execution. So for example, when we assign an expression into a variable, we evaluate that expression all the way down to a result before we do the assignment. Similarly, when we call a function, we evaluate the arguments before we perform the function call. The simple theoretical model for this is, of course, the call by value lambda calculus. Lazy strategies, on the other hand, operate differently. They only evaluate expressions when their results are actually used. So when we call a function, we don't evaluate the arguments until the arguments are actually used by the body of the function, if indeed they are. Similarly, when we assign an expression to a variable, we don't assign the result of that expression to the variable, rather we store a thunk, or a suspended computation, representing that expression. The simple theoretical models for this are the call by name and call by need lambda calculi. There are a variety of reasons why you might wish to use either of these strategies when implementing your programming language. Strict strategies tend to be more performant and more predictable, while lazy strategies are frequently more expressive, particularly when you're working with infinite-sized data, and can be faster in cases when you have lots of expressions whose results are only used on certain branches of execution. However, naively implemented, lazy evaluation suffers from a particular flaw. It uses a lot of memory holding onto the references to the various variables in use by the thunks in your program. So in practice, programming languages that want to implement lazy strategies will actually opt for a third approach, which is non-strict evaluation. This strategy straddles the boundary between strict and lazy by allowing expressions to be evaluated at any point between when they first appear and when they're used. In theory, this will give you both the expressivity benefits of laziness and the performance benefits of strictness. This is famously the evaluation strategy used by Haskell, and more infamously the evaluation strategy used by R. Okay, I'm going to put a pin in that definition for a moment. We will come back to it in a couple slides, but I want to briefly change gears to talking about another definition of strictness, which is as a characterization of variable usage. We say that strict usage of a variable is the kind that scrutinizes that variable. What does it mean to scrutinize a variable? Well, we're working in a lazy or non-strict setting, so variables can contain potentially unevaluated thunks, but certain ways that we might use these variables will require these thunks to be evaluated down to their top-level constructor. Think like adding numbers together, or branching on a Boolean value, or casing on a sum type. All of these require us to evaluate the contents of a variable down to their top-level constructor in order for us to know how to proceed with evaluation, what branch to take, something like that. This is what we mean by scrutinizing a variable. This is what we mean by strict usage. Lazy usage does not do this. This is using a variable in such a way that we don't need to scrutinize it in order to proceed. Think like putting a variable into a constructor or passing an argument to a function. An analogy that I find helpful is to think about variables like boxes that can contain potentially unevaluated expressions. Strict usage is the kind that opens the box, inspects the contents, and thereby triggers evaluation of those contents. Lazy usage, on the other hand, simply picks up the box, moves it somewhere else, frequently into a different box, but importantly does not open the box. So, given this intuition, we can take a look at some programs in a simple call-by-name programming language and ask how they use their arguments. In this first case, this function uses its argument x strictly. In order to proceed with evaluation of its body, we have to evaluate x and its contents down to either true or false. We can't know which branch to take otherwise. On the other hand, the second function uses its argument y lazily. The just constructor does not require us to evaluate the argument in order to accept that argument. We can simply take y and whatever suspended expression is inside of it, put it into the just constructor, and return from the function. Lastly, however, we have the identity function. And, well, the intuition that we have so far doesn't quite work here. It's going to be important for later that this is considered a strict usage of the variable z, but the idea that we have so far doesn't quite tell us why this should be so. And in order to understand this, we're going to need to take a step back and connect our usage-based definition of strictness with our evaluation-based one from earlier. As I said before, the semantics of non-strict evaluation only require that expressions be evaluated at some point between when they are defined and when they're used. In practice, though, if a programming language wants to actually implement non-strict evaluation, it needs to make a choice about where this evaluation is actually going to occur. And typically, languages will do this via strictness analysis. Strictness analysis posits a hypothetical laziest possible evaluation of any given program, and then asks which expressions in the program can I safely evaluate strictly or eagerly. Where safely here means without changing the observable behavior of the program relative to this laziest possible evaluation. Different languages might mean slightly different things by observable behavior. Think like throwing an exception or not terminating. What's important is that we don't consider things like memory usage or performance to be observable. Strictness analysis is allowed to optimize programs. To make things a little more concrete, let's take a look at some examples. This program here assigns the abort expression, which will fail the moment we evaluate it, into the variable x, and then we add 3 to x. This program will evidently fail immediately if we evaluate strictly. We will trigger the abort and fail. However, the program will also fail if evaluated lazily, just later during the addition, because the addition uses x strictly. We will need to evaluate x's contents here, thereby also triggering the abort. This program, therefore, has the same behavior in both a strict and a lazy evaluation. This other program, however, will behave differently if evaluated lazily. It will succeed, producing the value just x, where x contains a thunked abort expression. This will not fail because just doesn't evaluate its argument. It uses that argument lazily. So, in general, the key insight of strictness analysis is that the definition of a strictly used variable can itself be evaluated strictly, while the definition of a lazily used variable must be evaluated lazily. The connection between these two ideas gives us a unified definition of strictness, which we evaluate or express in terms of functions. We say that a function f is strict if and only if f of bottom equals bottom. Bottom here represents an expression whose value we cannot compute, whether because it throws an exception at runtime or because it doesn't terminate. The point is that if we give f an argument that we cannot reduce to a value, then the entire function call to f will also not be reducible to a value. This is the definition of strictness that you will most commonly see in the literature. I'm going to refer to it as extensional strictness for the rest of this talk, for reasons that I think will become clear momentarily. So with this new definition in hand, let's go back to our examples from before and ask, are each of these functions extensionally strict? Well, the first function is, if we pass bottom in as an argument, substituting for x, then we will be unable to evaluate the body because we cannot evaluate bottom to either true or false. Evaluation of the if statement will fail, f of bottom equals bottom, f is strict. G, on the other hand, is lazy. If we substitute in bottom for y, we will get the result just y. This is a constructor containing an aborting expression or a failing expression, but it is not itself bottom. G of bottom is not bottom, and therefore G is lazy. Then lastly, we can now more easily see why the identity function is strict, because it just directly returns its argument. If we give it bottom, we'll get back bottom. H of bottom is bottom. H, therefore, is strict. And this definition works pretty well. Compilers like GHC, for example, are able to use it to implement strictness analysis and recover much of the performance of strictness without compromising on the expressivity of laziness. However, the examples that I've shown you so far are almost trivially simple. Let's see what happens when we start adding a little bit of additional complexity to the programs that we're reasoning about. Let's take this Haskell program, for example. We might wish to ask, is this function extensionally strict in its arguments, f, g, and a? Well, the first thing that you may notice is that this uses a library function in its definition, the bind operator for the maybe type. And in order to even begin thinking about the strictness of this function, we need to know the strictness of this bind operator. And the only place we're going to be able to find that out is in the documentation. There's nothing in the program that will tell us this. And so we need to look at the documentation and hope that it will tell us, because if it doesn't, well, we're simply out of luck. If it does, well, then we'll know that this function is strict in f, but whether or not it's strict in G and A actually depends on the strictness of f itself. If f is not strict in its argument, its first argument, then this function will not be strict in A. And if f returns the nothing constructor instead of a just constructor, then G will never be called, and this function will be lazy in G. So we're going to actually have to inspect each of the call sites of this function in order to know what argument it gets for f, and therefore then be able to figure out its strictness with respect to its other arguments. So this analysis becomes inherently interprocedural, and ultimately we are forced to run what amounts to a mental abstract interpreter in order to figure out the strictness of functions. We need to substitute in bottoms for all the variables in our program and see what happens. And this is complicated, and as our programs grow and grow in complexity, it gets more and more challenging. It's also a little weird in cases like this one. This function is extensionally strict. Why? Well, it always fails, so it always returns bottom, and if f of anything is bottom, well then clearly f of bottom is bottom. But despite being extensionally strict, this function doesn't use its argument strictly, or at all. What's going on here? I thought there was supposed to be a connection between these two ideas. Something's a little bit weird. So at this point, it's worth taking a step back and asking, can we do better? Can we come up with a definition of strictness that more accurately captures our intuitions about what should be going on? Ideally, this definition will tell us more directly how arguments to functions are used. It will not require us to evaluate programs in our heads, even abstractly, and ideally also give us some reasoning principles about lazy functions. Right now, the extensional definition only tells us what it means for a function to be strict. Lazy functions are those that are not strict. We don't have any properties about them other than that they aren't strict. So we'd like a definition that gives us some meaning behind laziness. Well, the fact that I'm up here talking to you may suggest that yes, we can do better, and we do so via the definition of intentional strictness, which we name in opposition to the extensional definition because while that one is defined in terms of a function's inputs and outputs, this one is more about a function's definition and body. And this says that a function is intentionally strict if and only if it uses its argument strictly. This sounds a little bit tautological, so we can rephrase to say that a function is intentionally strict if and only if its argument appears in a strict position. And this language should clue you into the idea that this is a syntactic approach to thinking about strictness. In each case, we can inspect where a variable appears in the program, whether it's a strict or lazy position, to figure out how that variable is used. Here, y, for example, appears as the argument to a constructor. That's a lazy position. This function is lazy. Here, the return of a function is strict. This function is therefore strict. Here, the guard of an if statement is strict. Here, the argument to this function doesn't appear at all in the body. We characterize this function as intentionally lazy. This, of course, gets a little more complicated, as it often does when you start introducing higher order functions. We have this if statement here where the guard, as before, is a strict position, but the thing that appears there is the call fx. So whether this function is strict in its argument x depends again on the strictness of f itself. But unlike before, where we had no information available to tell us this, here we're going to get this information from the type of f. We're going to generalize this syntactic approach into a type and effect system that assigns each expression both a type tau and an effect gamma that describes the way that each program uses its free variables. Let's take a look at some examples. If we have some variable z with type tau in our context, then a bare usage of z will, of course, also have type tau, but it will also have an effect z strict that tells us that a bare usage of z is a strict usage of z. So far, so good. In the second example, we have x of type Boolean, and we have this if expression with type int that again tells us that this uses x strictly, because x here appears as the guard of the if statement. Here, however, Just y, when y has type tau, will have type maybe tau, but this expression will tell us that it uses y lazily. Y appears as the argument to a constructor. That's lazy. But the type of this expression will also tell us that if we unwrap this maybe type and inspect its contents, that will trigger a strict usage of y. In general, in the intentional framing, this type of an expression tells us how its free variables will be used as more and more of that type structure is scrutinized. If we close this expression via an abstraction, we can now see how the type, or the lazy annotation for y, moves off of the judgment onto the argument of the function, telling us that this function is lazy in its argument, but returns a value that will use that argument strictly if you unwrap it. A little bit of eta reduction, and we can see that this is the type of the just constructor, which, as I have said at many points now throughout this talk, is indeed lazy in its argument. And then last but not least, we have this function that discards its argument and fails, and we characterize this as intentionally lazy. Now this is, of course, different than what the extensional definition would tell us here, and so it's worth asking, given this difference, what properties are we actually capturing with this new definition? What does it guarantee about variable usage? There are two properties here that we are guaranteeing. First, that intentionally strict variables are always scrutinized during execution, and second, that intentionally lazy variables are never scrutinized during execution. There is a third intentional characterization of indeterminate for when we cannot statically know whether or not something will be used at runtime, but we are only going to guarantee properties about these first two. Stated a bit more formally, the first property is strict failure, which tells us that a well-typed program will always fail if one of its intentionally strict variables is missing. If we imagine that we can evaluate a program that's open with an environment that substitutes values in for free variables, if this environment is missing an entry for one of the strict variables, then evaluation of the whole term will necessarily fail. You can see the connection here with the original extensional definition because you can imagine closing this open term via abstraction and then think of the environment like arguments to this new function. If this environment is missing a value, that's like a bottom argument, and the failure of this term is like a bottom result. F of bottom will be bottom if this missing variable is strict. The other property that we get is lazy soundness, which tells us that a well-typed program will not fail because its intentionally lazy free variables are missing. And this gives us a new reasoning principle. It tells us that if an intentionally lazy function call does fail, it's necessarily not because of the argument. This is useful, say, to a hypothetical programmer debugging a failure in their intentionally lazy function, because they know that the source of that failure must be the body of the function. They don't need to go look at call sites, because the type system will tell them where the error must be coming from. And only intentional laziness is strong enough to guarantee this. Extensional laziness cannot, because this function here is extensionally lazy. This, depending on the value of its first argument b, will either return its second argument x or the number 2. So if we substitute in bottom for x here, we will either get back bottom or 2, depending on b. So given that f of bottom is not always bottom in this case, we must characterize this as extensionally lazy. In the intentional world, we prefer to think of this as intentionally indeterminate, better reflecting the fact that we don't actually know how x is going to be used at runtime. We also saw earlier that the intentional strict failure property sort of implies the original extensional definition, and this is reflected in the fact that all intentionally strict functions are also extensionally strict. And then, in the category of intentional laziness, we can see that there are elements that are in both the extensionally lazy and extensionally strict categories, reflecting the fact that these two definitions are fundamentally capturing different things. Intentional strictness and laziness are really about how functions use their arguments, while extensional strictness and laziness are about the values that they produce. So, what have we done here? What does all this buy us? Well, we have decoupled the definition of strictness from the observable behavior of programs. And this has a number of benefits. First, it's just easier to think about. Instead of having to reason about two related but distinct properties at the same time, we can now think about them individually. It gives us more powerful reasoning principles, as we just saw. It's more intuitive in cases like this one that fail irregardless of their argument. And also, because it's a type system, we can more easily surface it to users. One could imagine a programming language based on this that reflects the strictness of its functions directly in their types. Users wishing to know whether a function is strict could simply look at its type and not need to go consult documentation, which is, of course, fallible. This is, unfortunately, all of my time, but there is plenty more detail in the paper if you're interested, including formal statements of all the properties that I just presented here, the logical relations we use to prove them. Experts in the audience may be interested to know that we did all these proofs via an embedding into call by push value, which significantly simplified a lot of the reasoning here. There's a lot of redundancy in the cases of all the places where evaluation can be suspended. Call by push value sort of solves this problem by isolating all that reasoning to just the thunk case. We also have extensions to our type system to track additional information, and we mechanized all of this in Rocq. I am happy to chat in extensive detail about any of this afterward or take any questions that you may have now. Thank you so much for listening.
Hello, thank you for the talk. I was wondering about, so you've defined the strictness as a property of the function, but then in your explanation you track it in the judgment and also sometimes in the constructor, or sorry, in the type of the constructor. So I was wondering why this doesn't show up as a property of a function, as in you can give a function type which receives, it's an annotation of the function itself. So here you have it in this one argument, but then in the other ones you define it as something which is a property of the whole expression.
Yeah, so the effect, the gamma is a, the usage of all of the free variables in the term. So if there's no free variables, like in this fourth example, then there's no gamma. But when you close a term that has free variables via an abstraction, the gamma, like the effects that were previously associated with those free variables now move onto the argument of the function because, like, in some sense, the abstracted term and the one with the free variables are like related that way.
So what about the annotation in the maybe?
So that is describing the fact that the maybe, like this maybe type, will cause further downstream usages of y if you inspect it, like if you open it and then use its contents. So here, this function type is telling us that while we're lazy immediately when you call the function, if you then take the result of the function and then use that and inspect the return type of the function, that will cause downstream usages of the argument.
I was just thinking that in there, I would have expected this to be a property of the just constructor, where the just constructor is a function, and then when you match on the just constructor, you would unpack the information about the y. Oh, right, there you are. Very good.
Hi, thanks for the nice talk. I was wondering why you defined in the type system version of this the return position to still be a strict position. You motivated this initially with your semantic definition. You also showed why that definition is flawed, so this doesn't necessarily carry over to why in the type system you still treated that strictly.
Yeah, the return of a function sort of, if you want the semantic connection, in order to motivate any of this, you have to assume that you're actually going to use the result of your program when it finishes executing, right? If you don't ever use the result of your Haskell program, for example, nothing will ever run. So we have to assume that the program itself is inherently a strict, like the outer term of the whole program is a strict position, which means that a bare variable also necessarily becomes a strict position. And then when you, again, connect that to functions via abstraction, that means the return of the function is also a strict position.
Okay, thanks.
So if I understand it correctly, so you need to record every free variables in each type constructor. So does it cause efficiency issues? Because basically your types will grow as your program size grows, and you need to duplicate these free variables for every layer. So have you done some maybe empirical evaluations on whether it?
We have not implemented this. Yes, the short answer to your question is yes. There is a very large annotation burden in this system. As presented here, it's more of a reasoning tool for like a new definition of strictness as opposed to like a practical proposal for a way that you could implement this. There is promising work in related areas of like how to reduce the annotation burden when you're tracking free variables like this. We haven't implemented that, but I think that is an interesting direction for future work to try to actually make this practically implementable.
Just a quick follow-up question. So is that true that you really need to duplicate everything for each layer of the type constructor, or that it can be collapsed or something?
That's sort of the question, is like, is there any redundancy that we can eliminate to make this a simpler problem, basically?
Yeah, okay, thank you.
All right, maybe a last question quickly.
Yeah, you mentioned that program optimization is one of the main applications of strictness analysis. So just wondering, does your new definition of strictness allow for more opportunities for optimization?
No, probably not. I think I don't have like a formal, like we've proved that it doesn't, but my guess is no. The benefit, I think, is that if you are a programmer trying to figure out why your Haskell program, for example, is not optimizing the way that you want it to, the only way that you can do that right now is to like basically dump the output of GHC and inspect what the compiler is telling you, and that's not particularly pleasant. So the motivation for this is like to come up with a way of thinking about strictness that's easier for people as opposed to like enabling more compiler optimizations.
Makes sense. Thanks.
Okay, thanks again.